Imagine, for a moment, two tiny particles. They are born from the same event, a single fleeting burst of energy in the cosmic dark. Now, let's separate them. We send one particle to the farthest edge of our galaxy, the Andromeda Galaxy, millions of light years away. The other remains here, in a laboratory on Earth. They are now separated by an unimaginable void, a distance so vast that a message, even traveling at the speed of light, would take millions of years to cross. According to the laws of physics as we've known them for centuries, these two particles are now entirely independent. They exist in their own separate realities, governed by their local environments. What happens to one should have absolutely no bearing on the other until a signal can bridge the gap. But the quantum world operates by a different, more mysterious set of rules. Here on Earth, we decide to measure a property of our particle. Let's say its spin. The moment we observe it, it settles into a definite state, pointing up. Instantly, at that exact same moment, its distant twin in Andromeda, which could have been pointing in any direction, immediately settles into the opposite state, pointing down. There was no travel time, no signal was sent, no message traversed the cosmic expanse. It is a connection that seems to defy the cosmic speed limit, the speed of light. It's as if the universe itself maintains a hidden, unbreakable thread between them, a private conversation that bypasses space and time entirely. This bizarre, instantaneous link is what Albert Einstein, unsettled by its implications, famously called spooky action at a distance. It's a phenomenon that challenges our deepest intuitions about reality, suggesting that the universe is far more interconnected and far stranger than it appears. This is the story of quantum entanglement. Quantum entanglement isn't just science fiction, it's one of the strangest and most real phenomena in physics, and it challenges everything we thought we knew about reality. To understand entanglement, we first have to journey back to the dawn of the 20th century. Physics was in turmoil. The classical, predictable rules laid down by Isaac Newton, which perfectly described the motion of planets and falling apples, were breaking down. When scientists tried to apply these same rules to the universe at its most fundamental level, the realm of atoms and their constituents, the math simply didn't work. A revolution was brewing. Pioneers like Max Planck and Niels Bohr began to sketch out a new, radically different picture of reality. In this quantum world, particles like electrons and photons weren't just tiny solid balls. Instead, they behaved like ghostly waves of probability, described by a mathematical concept called the wave function. This led to one of the most mind-bending ideas in all of science: superposition. Superposition means that before it's measured, a particle doesn't have a single definite property. It exists in a fuzzy blend of all its possible states at once. Imagine a spinning coin before it lands. Is it heads or tails? In a way, it's both simultaneously, a blur of potential. For an electron, this could mean it's spinning both up and down at the same time. It's not that we don't know its state, it's that the universe hasn't decided yet. This cloud of possibilities only solidifies into a single concrete reality at the exact moment of observation. The instant we measure the particle, the moment the spinning coin lands, the wave function collapses and the particle is forced to choose one state. This bizarre concept was famously illustrated by Erwin Schrödinger's thought experiment with his hypothetical cat, which would be both alive and dead inside a box, its fate tied to a quantum event, until the moment someone looked inside. This principle, that particles exist in multiple states until observed, is the first crucial stepping stone on our path to understanding entanglement. So, how does this strange connection, this quantum entanglement, actually work? Let's move beyond the analogy and look at the fundamentals. Imagine a process where a single stationary particle decays, creating a pair of new particles that fly off in opposite directions. Because of fundamental laws of physics, like the conservation of momentum and angular momentum, these two new particles are not independent. Their properties are intrinsically linked from the moment of their creation. They share a single unified mathematical description, a single quantum state, even as they become separated by vast distances. Let's consider a property called spin, which you can loosely visualize as a particle's intrinsic angular momentum. For our purposes, let's say a particle can be either spin up or spin down. Before we measure them, each of our entangled particles exists in an uncertain state of superposition, a ghostly blend of both spin up and spin down simultaneously. Neither has a definite spin. However, their shared state dictates a perfect anti-correlation. If one particle ends up being spin up, its partner must instantly be spin down, and vice versa. This rule is locked in from their birth. Now for the truly bizarre part. Let's say we wait until these particles are light years apart. An observer, let's call her Alice, decides to measure the spin of her particle. The moment she performs the measurement, the superposition collapses. Her particle is forced to choose a state. Let's say it resolves as spin up. Instantly, across the cosmos, the other particle, observed by Bob, simultaneously resolves into the spin down state. It's not that the information traveled from Alice to Bob. There was no signal sent. The outcome on Bob's end was determined the very instant Alice made her measurement. This is the heart of what Einstein famously called spooky action at a distance. It's a perfect correlation, happening faster than light, because the two particles were never truly separate entities to begin with. They were always two parts of a single interconnected system, described by one indivisible reality. Einstein didn't like this. He believed physics should be local, that information can't travel faster than light. But quantum mechanics seemed to say otherwise. In 1964, physicist John Bell developed a way to test whether entanglement was real. His Bell's theorem showed that quantum mechanics could predict correlations no classical theory could explain. Decades later, real-world experiments proved it. Entanglement is real. In 2022, the Nobel Prize in Physics was awarded to scientists who showed quantum connections are stronger than any classical logic. Today, entanglement is more than theory, it's technology. Quantum teleportation allows us to transfer information instantaneously between particles, paving the way for the quantum internet. Entanglement forces us to ask, what is reality? If particles can influence each other instantly, is the universe more connected than we ever imagined? Quantum entanglement. It's not just spooky. It's the universe whispering that distance might be an illusion, and that everything is part of one grand design.